Okay. Oops. Sorry. Thanks to the organizers for giving me a second chance to atone for my sins of not talking about lensing in the morning. I'll try to make it very short. So this morning I tell you about the degravitation part of the story. So now I'm going to tell you a little bit about magnification bias. And perhaps you can think of this as kind of an introduction for much more interesting results by Breeze and Ryan that they will talk about tomorrow. I'll just give you a very quick overview. You probably all know this. The effect is very well known. It's been known for a long time. So imagine these stars as representing galaxies that you have in the survey. And imagine between these galaxies and the observer, which is us, there's a large mass concentration. Then qualitatively, there are two effects going on. One is that these galaxies would be magnified. They will be brighter, larger, and further apart. So that decreased the number density of galaxies in that direction of the sky. The opposite effect is that faint galaxies that are represented by these dashed stars that you otherwise wouldn't have seen, now they are in your samples. So that increased the number density of galaxies that you see in that direction. And in general, these two effects, to what extent they cancel each other, depends on the number count slope at the threshold of your survey. So this is called magnification bias. A lot of people in this room have worked on this subject. What I want to just very quickly tell you a few projects that we have been doing that have maybe not so often discussed, but they are, if you just spend a few minutes thinking about it, they're more or less obvious. Consequence of magnification bias. I don't think I'll talk about the third. In some sense, that's what Gary talked about in his talk, that magnification bias actually affects lensing measurements in general, in particular galaxy lensing measurements. I won't talk about that at all. So let me just focus on the first two. The first is that magnification bias actually has a large impact on ISW measurements, integrated Sax-Wolf measurements. It's actually an order 1 effect in the following sense. So let me just step back. What are ISW measurements? So this is the large scattering surface. This is the observer. You have galaxies down here. The temperature and isotropy that you see have several contributions, one of which is the well-known ISW, which is basically an integral along the line of sight of the time derivative of the potential, the gravitational potential. And if you have a universe that has only matter, no curvature, no dark energy, then this on large scale should be 0, and so this term should be absent. And if you have a universe that has dark energy, for example, this term would be non-zero. And the way you would isolate is you cross-correlate the microwave background with galaxies in the foreground, which would be correlated with this potential at low redshifts when the universe starts accelerating. And this was something that was proposed a long time ago, and there were very nice measurements by Ryan and also by Enrique Gastillaga on actually detecting this signal. So this has been detected over actually a pretty wide redshift range by now with high significance. So what does magnification bias do? It's very simple, actually. So here's what it does. Let me step back here for a second. So if you cross-correlate microwave background with galaxies at progressively high and high redshift, eventually you'll be back in the matter-dominated regime where this is small or close to 0. And so eventually your natural expectation is if you do this cross-correlation measurements of galaxies and microwave background, eventually when you move to sufficiently high redshift, it should go to 0. But magnification bias is basically going to alter that expectation for very simple reasons. Because if you cross-correlate microwave background with galaxies at high redshift, these galaxies are always modulated by gravitational lensing, i.e. due to magnification bias, which means when you are cross-correlating microwave background with galaxies at high redshift, in some sense you are secretly, without knowing it, cross-correlating microwave background with actually matter fluctuations at low redshift, for which the universe is accelerating and hence phi dot is non-zero. And so, in fact, as you look at galaxies at higher and higher redshifts and cross-correlate them with microwave background, you would actually see that your signal not only does it not decrease, but in fact, you would expect the signal in general increases for several different reasons. One of which is, usually when you look at galaxies at higher and higher redshifts, you're looking at galaxies that are intrinsically brighter and brighter, which means their number count slope is steeper and steeper, which actually makes the gravitational lensing, the magnification bias correction actually larger and larger. And also because by making your sources going to higher and higher redshifts, you have basically more lensing efficiency. So the two add together. Again, it's a sample-dependent question, but in general, in fact, you would expect that beyond about redshift of, it really depends on sample, but roughly speaking, beyond redshift about 1.5, you should actually start to worry about the fact that what you are seeing is actually cross-correlating microwave background with that meta fluctuation at low redshift via magnification bias. And so once you just take this into account in interpreting data. Okay, so it's a very simple point. I'm going to skip on this. And then let me move to the second point, which is also more or less obvious, if you think about it a little bit, that a magnification bias in general would make your galaxy correlation function anisotropic. It creates something that actually looks like a finger of God on very large scales. And here's how it works. So this is the observer. This is the transverse separation. This is line of sight separation. And think about how one goes about measuring the two-point correlation function. You do this by basically doing pair counts of galaxies. And let's say I'm interested in pair counts of galaxies at some separation. Let's pick 100 megaparsec, for example. I could count pairs along the line of sight or transverse in the line of sight. And if you think about it, in this orientation, the foreground galaxy at some level could lens the background galaxy, whereas in this orientation, the lensing effect is much more suppressed, which means when you actually count pairs, it's going to be orientation dependent. Again, a very simple effect. And even though naively one might think this is a very small effect, if you think about it, in some orientation and in some at some separation, this is actually dominant effect. In the following sense, yeah. If you let's say you look at two galaxies separated along the line of sight in this orientation, as the galaxies get more and more widely separated, the intrinsic correlation between these two galaxies drop with separation, as you expect. On the other hand, the lensing correlation between these two galaxies actually increase with separation. In fact, the lensing correction is 0 if the lens at the source are at 0 separation. If you move them further and further apart, in fact, the lensing contribution increases with that separation. And you know at some point that has to win over the intrinsic signal, which drop with separation. And in fact, by about a separation of about a few tenths of megaparsec, the lensing contribution win. By the time you get to baryon acoustic oscillation scale, 100 megaparsec, this actually dominates. Again, it's not a small effect. It's order unity effect in this orientation. So let me show you kind of an illustration. It's these plots that large-scale structure people often make this pi sigma diagram. So this is transverse line of sight separation. This is this is transverse separation. This is line of sight separation. And what is being plotted here are basically contours of constant two-point correlation function. The dotted curves is without this lensing effect, and also ignoring for the moment peculiar motion. In that case, the contour should be basically circularly symmetric, as they should be. And if you include this lensing effect, magnification bias, what you would see is this solid contours. The red line here is basically the 0 crossing scale. That's the place where the two-point correlation function crosses 0. And you can see this is not a small, this is actually not a small correction, especially if you look in this direction. The contours is distorted by a lot. It looks like something like a finger of God. The two-point correlation function is enhanced along the line of sight, but this is a finger of God on very large scales, hundreds of kilometers, hundreds of megaparsec. And this effect is not concentrated only along the line of sight either. Even if you move away, at let's say this orientation, you can still see it even by eye. Of course, the effect becomes much smaller if you look at in the transverse direction. And this is at a mean redshift of 2. In case you think this is important only at sufficiently high redshift where the lensing efficiency is high, and let me show you what happened at redshift 0.35, which is where people have done these LLG measurements. The effect is certainly smaller, but you can see it's certainly visible even by eye here along the line of sight orientation. The question is whether this can be pulled off the data. So a few points I want to emphasize. So again, your observed number counts or number density of galaxies is equal to the intrinsic one plus the correction due to magnification bias. You square this to get the two-point correlation function, and so clearly you have 4 terms. 2 of them are just the cross terms, so they are grouped into one. One term is just the intrinsic clustering signal, galaxy clustering, and that if you ignore anisotropy to the peculiar motion, depends only on basically the net separation. This is line of sight separation and transverse separation. The galaxy mass or the galaxy magnification correlation function has this particular form. It's linearly dependent on the line of sight separation to lowest order, and times some function that depends only on the transverse separation. And then the mass-mass correlation to lowest order actually only depends on the transverse separation. And this is actually very generic. It's a generic prediction of lensing. It doesn't depend on whether you're assuming linear bias or not. Doesn't depend on the value of the number count slope. This is actually a pretty generic prediction of lensing. And because of this distinctive shape, you have an interesting opportunity, which is, given measurements of two-point correlation function, you can actually simultaneously fit for all 3 things and learn things about galaxy clustering, galaxy mass correlation, and mass clustering. And this is an experiment you can do in some sense without actually using galaxy shear information. This is just counting galaxies. So that's an interesting thing to do, just to make a connection to measurements that you might be more familiar with, such as the ones that Ryan Scranton and collaborators have done, is when people look at angular clustering, for example, when you cross-correlate quasars at high redshift and galaxies at low redshift, essentially what they are doing is they are taking the limit when this is very large, the line of sight separation is very large. And so you are basically dominated by just this term. This term is small, and so is that term. But if you go to actually smaller separations where the line of sight separation is not so large, in fact, all three would be present, but you actually know from lensing theory what the shape should be, so you can actually just fit for all of them. This also presents a little bit of a challenge for acoustic oscillation measurements in the following sense. If you actually zoom in on the appearance of these baryon wiggles, let's just look at the lowest 2 panels. This is the two-point correlation function as a function of separation. This is all in the line of sight direction where this effect is the largest. And this is zoom in around the wiggle. And this is without lensing, and this is with lensing. And you can see certainly the shape changes. By eye, you can see there's a subtle shift in the position of the peak. And in fact, if I had plotted things slightly differently, instead of the two-point correlation function, I plot the distance squared times the two-point correlation function, which is sometimes plotted in these papers. You see that by eye, it almost looks like the one with lensing modification, the peak actually completely disappeared. The point of showing this is to warn you that exactly how lensing actually change your interpretation of where the peak is depends on how you fit for the peak, whether you're looking at this or this. So what I'm going to show you next is I'll just basically do the most simple-minded thing. Let's ask where the local maximum is and how much does it actually change, which is in the next figure. This is in the line of sight orientation again, where the effect is the largest. And the effect depends on this combination of parameters. 5s minus 2, this is what Gary talked about in his talk. S is the number count slope. B is the galaxy bias. If S has the fortuitous value of 0.4, then the effect is exactly 0, so it's here. This is the fractional change in the height of the peak, the width of the baryon peak, and the location. If you're interested in using it as a standard ruler, the most interesting is this number. The different colors correspond to different mean redshifts of your survey. Interestingly, in the line of sight direction, it's actually not very sensitive to the mean redshift of the survey, and the shift it really depends on this parameter now, but within reasonable range, it's about 2%, let's say. To give you one guidance on the value of this number for LLGs in the Sloan sample, this number is around 1, so it's about 2%. And 2% shift, while seems small, it is actually significant for dark energy measurements. It corresponds to 10% shift in W. If you try to use the location of peak in the redshift direction to infer the Hubble parameter, the expansion rate, if you don't account for this, your W will be off by 10%. This is in the line of sight direction where the matter is worse. If you look at transverse directions, it's going to be better, and so one way to show it is to just do a monopole. If I actually do a monopole, average over directions, the effect is much smaller. This is basically the same plot for the monopole. Now it actually really depends on the redshift, the mean redshifts. But in all cases, pretty much the shift in the location of peak is less than 1%. So this, more or less, I think the moral here is that if you use baryon acoustic oscillation if you're interested in using that as a standard ruler, you should be worried about using it to infer the Hubble expansion parameter, h of z, but probably not so much for the angular diameter distance, which is in the transverse direction. Okay? But again, this is not a showstopper though, because you know exactly the shape of this anisotropy. So the thing to do really, I think, is just to fit for it. You can actually fit for it and just remove this anisotropy. And you will learn extra things. You will basically measure these two things, which is nice. So I don't think I'll say more about this. And I'll stop here. Thanks.
Okay, yes.
So, principle that I'll prefer a W of less than -12.
Yes.
Can this sort of thing cause that?
If you look at their measurements, at least so far, the published measurements on W using baryon acoustic oscillation all use the monopole. And that effect is really fairly small, especially at this kind of low redshift that have been used so far. So I don't think it is terribly important for the current measurement that use monopole at redshift of, let's say, 0.35 up to maybe at best 0.6. It's okay. Whatever discrepancy that people might have found between, let's say, 2DF and SDSS cannot be explained by this.
If you use the monopole at, say, redshift 4 or redshift 3, this better?
Well, I showed you this plot, right? So it depends on then the level of accuracy you're interested in. This is the monopole. And so this is redshift 3, 2, 1.5, 1.35.
So has this been measured? I mean, in principle, could it be detectable in current data?
Very, very good question. It has not been measured.
But it should be detectable, right? Because it's very large scale. Yeah.
This is 0.35, so we certainly have, Sloan has data at this redshift.
Right.
This is very focused along the line of sight direction.
So you use a lot of modes. Like you've got very
There are
few
not a
modes.
lot of modes, so the question is there sufficient signal to noise to pull this out of the data? It's unclear, but it's work in progress. It's unclear.
Trace?
I was going to ask what the quadrupole looks like because if one is fitting for both an angular diameter distance at a Hubble constant,
Right.
really the monopole and quadrupole that
Right.
we use, then specifically along the line of sight.
Yeah, we have plots of the multipoles in our paper. Unfortunately, I don't have it here in the slides. But basically, because the form of the anisotropy goes like this, in fact, unlike, for example, Kaiser distortion, which is described by just a few low order multipoles, this actually have all higher multipoles. And in fact, if you go to quadrupole or the higher multipoles, it actually doesn't actually decrease very much. And so I think the best way to actually describe this anisotropy is actually just in this form, instead of fitting for multiples. Just fit for this form and take it out if you are not interested in these two terms.
All right, so let's thank Lam again.